Enemy radar is hot again. Triangulating E-lint sensors.
Activating SAR. Target identified.
Roger.
Crystal 1-1, you are clear to engage.
Weapons away, 25 seconds to impact.
Good afternoon. My name is Andrew Adams, and this is my course project video presentation for Dr. Wu's pattern recognition class at the University of Florida. The video clip you just witnessed demonstrates the powerful intelligence, surveillance, reconnaissance, and ultimately targeting capability of modern airborne weapon systems, especially with the recent advancements of unmanned aerospace systems. However, as you saw with the video clip, there still remains a very manned, labor-intensive part of this process. The ability to automate this process as much as possible will save valuable time and manpower on the fast-paced modern battlefield. This course project demonstrates how to create a classifier to conduct automatic target recognition using multiple inputs from multiple spectra. Now let's step through the briefing and we'll see how to achieve this. The project breaks down into 4 functional areas: sensing, taking your inputs from your sensors in the various spectra; feature extraction, taking that complex sensor data and breaking it down into the most key features which will give you the maximum amount of classification benefit with the minimum amount of information. Next, the classifier itself, which will classify the test inputs as either rotary winged aircraft, fixed wing aircraft, or armored vehicle. It achieves this by taking the training matrix and clustering that data in multi-dimensional space, creating decision regions around each one of those clusters, so that then when the test data comes in, it can put it into the appropriate class of either rotary winged aircraft, fixed wing aircraft, or armored vehicle. Finally, the system performs post-processing to perform additional analysis to get it into the most beneficial form for the user. Sensor data originates from 4 different sources: white light imaging sensor, an infrared or thermal imaging sensor, an acoustic sensor, which for this project represents the more commonly used signal intelligence electromagnetic sensor analysis, but because of the sensitive nature of that information, this project kept it to the acoustic realm and analyzed it in the frequency domain. And radar data, which can come from very precise imaging sources such as synthetic aperture radars, and it can augment your white light and thermal imaging, but it also can give you some additional information, such as in the case of this project, radar cross-section. The feature extractor has these 5 algorithm components: rotor identification, which gives you a rotor count; an affine or line analysis analyzes the basic shape features to give you a shape ratio; thermal imaging, which analyzes the heat sources in the object, give you a peak temperature; and spectral decomposition of your acoustic data to give you a primary audio frequency; and radar imaging to give you a radar cross-section. Feature extraction process started with sensor data from white light imaging, examples of which are on the top row. It took many more than these. These are just representative samples. And the first step involved just converting the image to black and white for processing. The first algorithm that it executes is the rotor identification algorithm, which basically looks for long, spindly features of your object. Basically defines an inner and outer boundary at the extremities and then rotates that region around, looking for areas of present or not present as the image rotates around. And this identifies the number of long spindly features, very much like helicopter rotors, which are a very telling feature for defining the object. And in this case, it boils all that complex data down into one number, a rotor count. The next algorithm involved an affine or line analysis to identify the major line features and shape features which define each image. It achieved this by first executing edge detection using a Canny algorithm to outline the black and white image. Then it executed a Huff transform, which identifies each point along the perimeter of the edge and defines all of the lines passing through that point in accordance with the listed equation. Each point, x0 and y0, has lines passing through it that are defined by the r and theta of that equation, which equate to a sinusoidal curve for each one of the points. The Huff transform then takes the accumulation of all of those curves, and where they overlap the most, that indicates the areas of highest concentration of lines in the image. And here's the final product of that analysis. It generates the major line features of each object, and it determines a shape ratio, which gives you one number again that boils that entire very complex image down to one general shape characteristic. It does this by analyzing the angular differences between each line and every other line. The next algorithm involves thermal imaging, and in this case it is just a user entry due to the limited amount of thermal data available. With actual intelligence data, the algorithm would go through and analyze the image for gradient and determine the areas of local maximum peaks, and from that extract the actual temperature value, and also analyze the relationship from one region to another to determine spatial relationships unique to that particular image. But that analysis is beyond the scope of this effort. The next area involves taking an acoustic input and passing it through a fast Fourier transform to determine the primary spectral component. And again, it will take that sound data and boil all that complex sound data into one number, a primary audio frequency. However, due to the limited amount of audio recordings of different systems, it also allows the user the ability to enter that data as well. The last sensor source is radar data. This actually proved to be the most difficult sensor data to find even representative samples of. So in this case, for this project, it is just a user-entered value of radar cross-section. In reality, sample images such as this synthetic aperture radar image could go a long way to augment your white light and thermal images, especially in areas of obscuration with bad weather or camouflage, where your image is not the perfect white light image you would like it to be. On to classification. The system then takes all of that training data from the extracted features of each one of its entries and creates a training data matrix. It will then take that data and cluster it into groupings multidimensionally, create decision boundaries around those groupings so that when the test data comes in, it will have the appropriate region in which to put the test data. When the test data comes in, it actually goes through the same analysis process that the training data went through in order to extract the same features. And in this case, we had a particular target, and these were the numbers for rotor count, shape ratio, peak temperature, acoustic frequency, and radar cross-section that were generated by the system. A second target, similar to the first, different numbers and different analysis. And a third test target. Two separate training data matrices were generated for this project. For the first, it used the data that was generated from all of the sensor algorithms in MATLAB. However, because the numbers of system training data inputs were relatively few, in this case 9, another separate matrix was used which simulated larger amounts of data. Here's the first matrix, here's the second, indicating the simulated data. After going through classification, as you would expect based on the images you see, under both circumstances, the system correctly classified each target. Target 1, fixed wing, target 2, armored vehicle, target 3, rotary winged aircraft. Following classification of the system into its appropriate class, fixed wing aircraft, rotary wing aircraft, or armored vehicle, the number of possible exact matches drops significantly. So that's where post-processing comes in. In this case, the system analyzed a length to width ratio and just applied it to a lookup table, and as a lookup table is beyond the scope of this effort for all possible systems, the system just compared it to the actual known measurements of each system. As you can see here, the length to width ratios were very, very close, allowing a very precise match within each target class to be made for each system. Now, we will move on to a MATLAB demonstration of all these features. Now I'll demonstrate how to first enter training data. We'll use an F-16 as the representative system. And it will go through all the algorithms we mentioned before. Going through the rotor count. And obviously, other than the extended fuselage, there is not really much to speak of for any spindly type features. Now it's going to ask for the manually entered data. We can actually enter some acoustic data if we choose and have it perform that analysis. And now it asks us to enter all of the other manual entries. We can pick arbitrary figures here. And now we can move on to actually demonstrating how to enter a test target. In this case, we can use an Mi-24 helicopter and have it perform a similar analysis. We'll again go through and extract all the features like we demonstrated before. And it will then take all these entries one at a time and build your initially training database, and then it will build your test case from these manual entries, and then it will go through classification. Now we'll execute our classification algorithm using the algorithm training data. And when we do that, as you can see, it generates target class 1, which corresponds to the rotary winged aircraft category. It had the training data from all of the algorithm entries and the prior distributions of 50% of the targets as rotary winged aircraft, 30% of the targets as fixed wing aircraft, and 20% of the targets as armored vehicles for this particular prior distribution. This project demonstrated the essential features of an effective airborne automatic target recognition system. It analyzed sensor inputs, it extracted the appropriate features, it performed classification into the appropriate class, and then performed post-processing to demonstrate the capability to uniquely identify each specific system. This is an exciting area of study with a lot of potential in the future, and I look forward to covering it more with future projects. Thank you very much.